Alright guys, another related rates problem. The fish population represented by big N in a small pond depends upon the number of pounds of algae, which is represented by little a, it contains. If the quantity of algae is increasing at a rate of 2 pounds per week, at what rate is the fish population changing when the pond contains 5 pounds of algae? A lot of words in this question. Now the population, in other words big N, is given by this equation. N equals that whole mess. 3a squared minus 20a plus 26 all raised to the fourth power. Okay, so what we're going to do is what we've been doing in every single question, and we're going to be rewriting a and n in terms of, we're going to relate them to t, okay? Because note that the amount of algae in the pond is increasing as time passes by, which means that as time passes by, the amount of fish will probably be changing as well. So let's take a look at what this looks like. So here I have created two graphs. The one on the left represents the number of algae over time, and the one on the right is the population over time. So let's just look at the one on the left right now, okay? So what do we have? A lot of this is, well, most of this is from the given question. So what they tell us is that at a certain time, I called it in this example, in my version, T0, T naught. At a certain time, T naught, the pond contains 5 pounds of algae, right? So at some time T naught, there's 5 pounds of algae. So that's what I marked right here. That's this point right here. And the other thing I'm going to mark is that they tell us that the algae is increasing at a rate of 2 pounds per week. It's increasing 2 pounds per week. Actually, that is dA dt. It's this guy. It's the slope of this curve. It's increasing at this rate, so we know that dA dt is equal to 2. So this is what we're given so far, at least for the A part. Now let's look at N. So N, on the other hand, notice how everything on the right-hand side of N has an A. Well, almost everything has an A in it. But these A's, like what we said in the previous graph, these A's are dependent on T. So what I did was, instead of saying N of A, I said N of A of T, right? So it's like a function inside another function. So I did that because the reason why I did that was so I can have a T down here as my horizontal axis variable, rather than having an A. So just like how at some time T naught, I had 5 pounds of algae, at some time T naught, I have N of A of T naught amount of fish in there. So the big question is, what does this guy equal? Well, A of T naught is equal to 5. That's what we said right here. A of T naught is equal to 5. So if I just plug 5 into this equation, I'll get the amount of fish. That's what I did right here. I plugged in 5 into my equation, and I got, at time T naught, there is only one fish in my pond. Okay, the last thing that we should talk about is this. What is the question even asking us? At what rate is the fish population changing when the pond contains a certain amount of algae? So the pond has 5 pounds of algae at time 0. So at time 0, what does the population look like? Well, we already calculated that it's 1. What they want us to calculate is what is the rate of change of the fish population, meaning what is the slope of the tangent at that point? And that slope of the tangent right there is represented by dn dt. Okay, so we have a lot of things already figured out or given to us. We don't have to do much work, honestly, for this question. So we're trying to figure out what dn dt is. So what I'm going to do is I'm going to come down here, boom, and in order to find dn dt, I'm going to take the derivative of both sides with respect to t. Boom, right here. Okay. Notice how before I did that, I changed all my a's to a's of t's. So I take the derivative with respect to t on both sides. On the left-hand side, all I have is dn dt, which is what I'm trying to solve for. And on the right-hand side, I have kind of a mess. On the right-hand side, I have to use the chain rule because this guy is not, I don't have just a base of t, right? Meaning if I had d dt of t of 4, then this whole thing is just going to be 4t cubed. But because I don't have a base of 4, I have a function of t, I have to use the chain rule. So here's the chain rule applied in this next step. So remember, I drop the exponent, take 1 away from it, and I leave the inside function alone. And I multiply this whole guy by the derivative of this inside function. So as you take the derivative of that inside function, you're going to have to use some implicit differentiation, right? So the derivative of 3a of t squared is this guy, and this guy goes to 0, and the derivative of minus 20 a of t is just minus 20 dA of dt. Okay, so hopefully this should be pretty familiar to you guys if you watched my implicit differentiation videos or my chain rule videos or any of the other two related rates video. So what we're going to do now is we have this huge equation. What we're going to do is we're going to fill in the things that we know. So the first thing we know is a of t0, right? We set up here a of t0 is equal to 5. So everywhere I see a of t0, I replace it with 5. And the other thing we know is dA dt, the rate of change of the amount of algae, right? So we know that dA dt is right here. It's the slope of this line. So we can just fill in everywhere we see dA dt with just 2. Now, we have no more variables on the right-hand side, so we get that this whole thing, dn dt, is equal to 80. That means the slope of this tangent line right here is 80. All right, guys, hopefully that made sense to you guys. I think we have one more example left for this, and then we'll finally be done with related rates.